Hi everyone, I'm Jean-Marc Denis, the Chief Strategy Officer at Sipearl. I am very pleased to attend today to the HPC User Forum. In this presentation, I'm going to talk about Sipearl, the European processor company formed to realize the European Processor Initiative High Performance Processor. In this presentation, I'm going to provide an overview of Sipearl, and then I'm going to discuss the HPC system architecture and the resulting design elements and KPI for the Sipearl RHEA processor and how this determines our fundamental choices for the RHEA architecture. But let's start with the minute of classical Greek culture. At the beginning, they were Gaia, the earth, and Uranus, the sky. They got two children, Kronos and Rhea. Because Greek gods were a little bit special as a family, Kronos and Rhea got married and got 6 children. I should say 6 gods because they were very special people. And everything was okay. And the most famous of them was Zeus, the one we call the father of all gods. Indeed, Zeus had a very interesting life. I just don't understand why no series producer has made a multi-season blockbuster from his life, but this is a different story. At Sipearl, because we are going to use the ARM Neoverse V1 core, whose code name is Zeus, we decided to name the processor using this core RHEA. The other reason is that RHEA is our very first processor. All future processors that will be designed will be one way or the other RHEA child. Now, let's move forward and let's start the technical presentation. Sipearl was funded in June 2019 to design and to bring to market the high-performance European processor. We are a fabless CPU design company with HPC as our core target market. Seed money comes from different sources like Horizon 2020 or Horizon Europe. We are currently in Series A funding activities. Our first employee started in June 2020, and now we are about 50 employees. We are currently hiring 10 engineers every month for our design centers in Europe located in France, in Germany, and in Spain. We aim to create 1,000 jobs across several European countries by 2025. We are progressing well into the design of our first generation processor, RHEA. RHEA architecture is based on the ARM Neoverse V1 core. It incorporates in-package HBM for memory bandwidth performance and leverage the ARM Scalable Vector Extension SVE instruction set. At Sipearl, there are 4 pillars to support our value proposition. At first, a high-performance ARM server processor. A common platform to join RHEA with Accelerator is our second value, and this is extremely important, as I will explain later on. Then obviously, safety, security, and data protection are absolutely critical in the design of our processor. Last but not least, sovereignty is absolutely key for us to develop the European digital ecosystem. Our first processor, RHEA, is an HPC dedicated CPU, including ARM SVE, high performance bandwidth, memory, HBM, and a focus on secure and fully auditable solution. We choose the ARM Neoverse family for the performance of the cores and for SOC elements, but also importantly for the ARM server processor ecosystem. EU sovereignty is equally important for Sipearl. As the European processor solution, we want to grow the European ecosystem and value chain, ensuring that European funded projects can beneficiate from and generate new European technology such as acceleration, security tools, and so on and so forth. The flexible common platform is a good example of this, where Sipearl will work with European partners and beyond in a platform approach to closely couple acceleration with our general purpose processors. Finally, safety, security, and data protection are key European values. HPC markets are fairly basic security needs, such as secure boot, upgrade, and storage, but cloud and edge markets have different security requirements, and they are continuing to evolve, and we will focus our innovations in security, especially for those verticals. Now let's look at the strategic go-to-market we have at Sipearl. Sipearl very first market is high-performance computing, focusing on delivering the European EXASCALE systems. Our lead customers are the European HPC centers. We develop products based on European customer needs, then we market to the rest of the world. HPC market growth is accelerating due to the race to exascale, the proliferation of AI workloads, and the fast adoption of HPC in the cloud, which, according to Hyperion, has a 5-year CAGR of 25%, which is enormous. The European cloud market, including central and edge data centers, is also growing fast. The European Commission is pushing forward sovereign initiatives like Gaia-X and one IPCEI cloud and semiconductor initiative. European edge use cases range from 5G and smart cities to industrial edge and automotive. We will redesign our cloud processing performance for the appropriate market while innovating and securing advanced security features. Obviously, Sipearl doesn't work alone. ARM is a key Sipearl design partner, delivering their Neoverse solutions with their POP IP architecture. There is also the advantage of the ARM ecosystem, from toolchains and library support to driving customer awareness and education. ARM has a huge and growing presence worldwide, with nearly 200 billion processors sold so far. Focusing more specifically on the server market, there has been incredible growth in the last 5 years across Europe, North America, China, and Japan. ARM architecture is growing fast in HPC, of course. RHEA Fugaku supercomputer topped the HPC list last year, and the European Mont Blanc and CEA systems, and UK Isambard and Catalyst, in the US Sandia Astra and Stony Brook ARM systems, as well as other research systems, show that the ecosystem is driving new HPC business across the world. The other key partnership for us is obviously the European Processor Initiative. For Sipearl, this offers a wealth of design partners, end users, and IP providers for the development and distribution of the RHEA processor. The main EPI objective is to develop a complete EU-designed high-end microprocessor addressing supercomputing on edge HPC segments. A key element in our choice for ARM is the server and HPC ecosystem, the elements that go into system and sysdev. It is very, very important to consider that regardless the hardware considerations, what makes the difference, what makes the success of a new technology is the ecosystem, is the software ecosystem and how the end users and the developers will take advantage of this new hardware. What you see on this slide is quite important. It's very impressive on its own, but this is not an exhaustive list. You can see several logos. They represent hundreds of thousands of hours of developments, and there are millions of users of them around the world. And it's continuously growing, and there are new applications and developers working on ARM, especially in the server area. For instance, if we consider Calxeda, which is a US company that was founded in 2008, it's been the first ARM server processor company. The ARM server ecosystem is now considered mature, but it came 12 years after the start of the growth of ARM in the server area. It is now robust and growing independently. User groups, commercial companies, hackathons, consortiums all contribute to the growth of the ARM ecosystem. And if we focus now on HPC software stack, here is a breakout of the HPC software stack, and it's in generally speaking. Obviously, there could be some details not present on this slide, or some key code name that are not represented here, but I couldn't represent everything on a single slide. Again, this is clear that this is not exhaustive. But you can see that most of the critical HPC components are already present on the ARM ecosystem. The stack scales from platform-level software with operating systems, and this is developed by the processor vendors, by Red Hat, by the community with Linux, generally speaking, and it goes up to the application stacks, schedulers, tool chains, and management tools, all supported across the ARM ecosystem. Almost all proprietary HPC compilers are or will be supported on ARM. For instance, the Fujitsu compiler on scientific library, the RHEA one, and even the NVIDIA, which is considering that ARM is their next target as a supported platform for their whole stack. If the acquisition of ARM by NVIDIA is successful, and only if, it is very likely that CUDA will work natively on ARM as it is working now natively on x86. Obviously, this doesn't prevent us to develop our own optimized compiler backends of scientific libraries in order they are fully optimized for the RHEA processor and for next-gen processors. Now, if we move forward and we consider the evolution of the compute node across time. This slide shows processing trends over the last few decades. At the turn of the century, the majority of architecture were simple core, with performance gains coming from architecture on core microarchitecture decisions, but largely driven by core processor frequency. As frequency gains started to slow down, architectures parallelized and moved to multi-core designs for performance improvement. For roughly a decade, the growth in processor performance was driven by increasing core counts. And it's been successful. Huh? When power became a limiting factor, there was a further move to heterogeneous many-core designs using acceleration to boost performance beyond what general-purpose processor could support in an equivalent power envelope. In HPC, this included GPUs and accelerators like the Intel Xeon Phi, and today you have roughly 30% or even more of the top 500 list based on a combination between CPU and accelerators, and most of them being GPUs. And most are at the top end of the performance scale, and if you consider the top 10, 7 of them are acceleration powered, exclusively based on GPUs. At each wall, there is a natural resistance based on the ecosystem and software changes required to implement and maximize performance on the new architecture. Looking forward, we foresee the end of the current compute decade as a cost wall due to the slowing of the Moore's law and the increasing cost of lower geometry fabrication processes. This heterogeneous many-core decade is marked by the race to exascale computing. Other trends driving growth are the proliferation of AI and more recently the trend for global outsourcing to the investment in sovereign core competencies. Now, let's look at the trends in HPC to take us beyond the cost wall. Let's illustrate the current situation with several very famous upcoming examples. You can recognize here the new and future US EXASCALE machines. They will frame and structure the US HPC ecosystem for the next 3 to 5 years. They are all based on a SOC approach, tightly combining CPUs with GPUs from the same vendor, at the notable exception of the Perlmutter machine that is a prefigurator of the upcoming machines. There are obvious advantages using this proprietary SOC combination. At first, it's one vendor only. In second place, they are very homogeneous machines. And you can have advanced features like unified memory between the CPU and the GPUs. So, as a consequence, there is a better overall performance because of lower latency and increased bandwidth between the CPU and GPUs. And obviously, for the developers, having a unified memory combination could reduce the complexity to develop applications. But there are also some possible drawbacks to this approach. First, customers face only one vendor, and that could be problematic to some extent. So it's a one-fits-all approach. So how to address the extra large diversity of demand from end users? And you need to adapt applications and workflows to the specific architecture. That could be costly because of the time consuming aspect for the developer. It locks to some extent the end user into a proprietary hardware and software approach. And the mid to long-term evolutivity of this monolithic architecture based on SOC could be problematic with the evolution of applications toward very complex and heterogeneous workflows and data flows. Now, let's have a look on the trends in HPC to take us beyond the cost wall and beyond the usage of a proprietary SOC approach. The natural evolution we see in the European EXASCALE ecosystems, and especially for the European EXASCALE machines, is a focus on a modular system approach. The block diagram you can see at the center of this slide is a courtesy from the Jülich Supercomputing Center, which is a precursor of the modular concept in Europe. It explains quite well what will be a modular architecture in the future. The CPU module at the top of the diagram in green support the broad range of user workloads without requiring lengthy software porting and optimization. The booster module includes and incorporates GPUs for both floating point performance and AI training, provided there is a modification of the applications to take advantage of this architecture. And obviously, this kind of architecture can also easily incorporate other modules such as neuromorphic or quantum computing to further research in their very innovative domains. And they will contribute a lot to break the next wall in processor architecture evolution and in performance evolution. The value of this design is that each module can be independently scaled and upgraded, supporting a wide variety of workloads. The challenge for this type of system is the increased software and maintenance requirements for supporting the different modules. So this can be simplified by keeping a common CPUs across the modules, and that will make the whole difference. By definition, EXASCALE requires high floating point performance. Sustained 10 teraflop performance per node would require 100,000 nodes to meet EXASCALE, which is a large but manageable system size. We see systems larger than this, such as the Fugaku supercomputer, but their systems tend to be built with processors specifically architectured for the intended system, often to the detriment for use in a wider scale. The graph on the left-hand side of this slide is another way of viewing the modular architecture. As discussed previously, most EXASCALE systems will use acceleration, which typically means GPUs. GPUs are useful for lean-pack scores, but support a limited number of workloads, even if it is growing day after day. And the software model is complex to implement and difficult to migrate to a different accelerator. The flexibility of CPUs make them the workhorses across all required workloads. This requires a balanced processor with high memory bandwidth to deliver the data on processing performance to crunch it, meaning that HBM plus native accelerators for processing power with the appropriate memory bandwidth. The chart above shows this with increased flops along the x-axis serviced by GPUs, and the GPU providing a balanced performance measured here as byte per flop on the y-axis. The interesting part of this graph is the white space that dominates the center, which grows in relative size as we raise to EXASCALE. The white space emphasizes the modular architecture with different modules providing different capabilities along the two axes. Byte per flop is a very important KPI as a measure of the CPU portion of the system, since this is the module that will support all workloads. However, byte per flop is insufficient by itself, as you can drive the byte per flop up by driving flops down, which is not what we want in HPC. Gigaflop per watt is a very important KPI as well, but taken by itself, it encourages designs that target specialized accelerators and software optimized for lean pack at the expense of the majority of workloads. An important HPC metric is HPCG efficiency, which captures both memory bandwidth and floating point processing requirements. This is seen in the graphic on the right-hand side of the slide as the ratio of HPCG over RPEAK as a percentage of efficient system processing performance usage. The white space above the HPCG waterline up to Rmax represents system resources that is not optimized. Systems that focus mainly on high flop performance do poorly on this measurement. So, in conclusion of this chart, there are three KPIs: byte per flop, performance per watt, and HPCG efficiency, in addition to co-design with partners in the European Processor Initiative, are driving our RHEA architecture developments. Let's have a look on the Sipearl RHEA overall architecture. There are a lot of details I cannot share without an NDA, but we have chosen the ARM V1 core for our first generation for its excellent floating point performance on intelligent memory subsystem. The choice of the ARM instruction set is driven by performance, energy efficiency, and ARM's licensing policy on wide server software ecosystem. The memory current NOC, the NOC, is topology aware for design scalability and flexibility, scaling designs to fit multiple markets. With this architecture, we beneficiate from good computing element isolation and while supporting coherent SMP across CPU domains. Our memory subsystem includes both HBM and DDR linked to a generous last level cache. We also have high-speed I/O, including CXL2, CCIX, and PCI Express links to NICs and to accelerators on low-power die-to-die links. As far as I know, on the market, there is no other ARM-based HPC chip supporting CXL, and that will not be the case for the next years. We'll support CXL2 in RHEA, and with CXL, we'll be able to integrate most of the modern accelerators, offering very advanced features in memory management, like unified coherent memory. Specifically, the ARM V1 core includes 2 × 256 SVE engines, which can also be used as 4 × 128-bit Neon engines. This gives a tremendous performance boost at a low software overhead, as the compiler generates vectorizable code for the SVE engines. Generally speaking, the closer the offload is to the processor cores, the lower the software burden. ARM SVE engines support double precision, single precision, bfloat 16, and integer 8 workloads for vector processing or AI and machine learning. The choice of 256-bit vectors gives us a better trade-off of performance versus power per area for a number of reasons. Our average customer vector size is in the 300 byte range. As a CPU, we target HPCG efficiency across all workloads instead of lean pack performance on a limited number of workloads. This drives the efficient performance per watt and performance per area across all workloads. And this is a huge differentiator. In conjunction with HBM, SVE gives good performance on high byte per flop. Overall, the 256-bit vectors provide the best trade-off across HPC workloads on AI/machine learning. As mentioned earlier, Sipearl and the European Processor Initiative are also developing a common platform approach. The common platform decouples architectural requirements from the implementation by incorporating flexible memory, a current topology-aware scalable NOC, and the I/O. The common platform allows accelerators to be linked to the CPU and to beneficiate from the CPU resources. The flexibility that is coming with this also helps us to leverage various IPs from different product solutions. This graphic shows the concept of common platform. It incorporated 3 different ways to incorporate accelerators. At first, classical PCI Express connected accelerators. Then, coherent interfaces with CCIX and or CXL. And then we can have in-package connections or even IP designed in chip, closely coupled to the CPU. The goal is obviously to augment in-core acceleration, such as SVE, with look-aside acceleration that shares memory space within the CPU core and within the CPU space, the CPU memory space. So with this last slide, we are now at the end of the presentation. The final word will be to say that at Sipearl, we are very ambitious, very ambitious. We plan to be 1,000 by 2025. So join us, we are hiring. Thank you very much for your time.